Let's look at this derivative. We are going to find the derivative of f of x and then find the actual value of the derivative when x is 5 pi over 3. In other words, we're going to look for the instantaneous rate of change of this function at that moment, or the slope of the function at that moment. All right? So if you haven't tried this on your own yet, go ahead and try that, and we'll just go step by step. So of course, I'm taking the derivative of an exponential, so that's the derivative of the base, natural log of e, which is 1, times the exponential term as it is, and then the chain rule kicks in, times the derivative of the inside function. The derivative of sine of x plus 1 is the cosine of x. So now I'm going to substitute in 5 pi over 3, in for x, boom, boom. And now I have to remember my trig. So I always like drawing a picture, right? Here's my 30, 60, 90 triangle. 5 pi over 3. I always think of that pi as 180 degrees. So 180 degrees divided by 3 is 60 degrees. So I know my reference angle will be a 60-degree angle. 5 pi over 3, that's going to be in my fourth quadrant. You can either think of that as 60 degrees times 5, which is 300 degrees, or you can think of breaking up your 2 pi degrees into thirds. So there's 1/3 pi, 2/3 pi, 3/3 pi, 4/3 pi, 5/3 pi, which is where I want to be. If I kept going around, I'd get 6/3 pi, also known as 2 pi. Okay, so I know I'm in the fourth quadrant. I know I have a little 60-degree reference angle. You can call that rotating arm any length you like. Sometimes we use the unit circle 1. I personally like putting a 2 there because it just makes my numbers easier. The shortest side opposite the 30 is always half of that hypotenuse, 1 in this case. And the side opposite the 60 degree is always the short side times the square root of 3. Now, it's very important for us to look to see where we are and make sure we have positives and negatives in the appropriate spots. The rotating arm is always by definition positive, that's just length. My x is going to the right, so that's positive. My y is going down, so that is in fact negative. So that's a negative square root of 3, very important. Now I'm ready. So the sine of 5 pi over 3, sine is the y over the rotating arm, so that's going to be negative root 3 over 2. Boom. The cosine of 5 pi over 3, cosine is x over the rotating arm, so that's 1/2. And there's my answer. I just rewrote it and put the 1/2 in front, so it looks like a coefficient. And if you really want to be fancy, you can get a common denominator there with that 1 and rewrite your exponent as kind of one term, but that's not necessary. Okay, let's look at number 4. Remember, when you're looking for the slope of a tangent line, you're looking for the slope of the function at the point. In other words, you're looking for everyone together, the derivative of the function at that point. So let's take the derivative of this function. That's the natural log of e, which is 1, times the exponential term as it is, and then chain rule times the derivative of x squared, which is 2x. I'm finding a specific derivative of value at x equals 1, so I'm going to substitute in my 1, and that gives me 2e. That's my derivative, which makes it the slope of the function at that point, which also makes it the slope of the line that's tangent to the curve. Again, if you have a function, right, and you have a point, the tangent line is the line that skims along that function and has the slope of the function at that point. Now, also in this problem, I asked you to find the slope of the line that's normal or perpendicular to this curve. Normal in math also means perpendicular, okay? So if I'm looking for a slope that is perpendicular to a curve at a point, well, that means I'm looking for a line that is perpendicular to the line that's tangent to a curve at a point. So all we have to do is remember, how do I find the slope of a line that's perpendicular to another line? Well, the slopes are going to be negative reciprocals. So in this case, the slope of the line perpendicular to f of x at x equals 1 would be the reciprocal of 2e, which is just negative 1 over 2e. And let's look at number 7. Here's my function. I'm wanting again to find the derivative at a specific value, in this case pi over 6. If radians confuse you, remember that pi you can remember is equal to 180 degrees. So 180 divided by 6 is 30 degrees. So this is going to be a 30-degree angle. Let's take our derivative of each piece. Derivative of e to the 3x is e to the 3x times 3, chain rule, plus that 2 is a coefficient, so it hangs out. The derivative of the natural log of something is 1 over that something, and then chain rule times the derivative of that something. The derivative of cosecant of x is negative cosecant of x times cotan of x. Okay? If you forget that, you can quickly rewrite cosecant of x as 1 over sine and do the quotient rule. Believe it or not, that's what I do every time. I'm not a memorizer. Hey, look, why are those crossed out? It looks like I put this over 1 and I'm simplifying. I can divide out those cosecants. Don't forget that negative is still there. So I can simplify this a bit before I go any further. 3e to the 3x minus, there's the negative times the 2, minus 2 times the cotan of x. Wow, that really got simplified nicely. Now it's time to substitute in my pi over 6. 3 times e to the 3 times pi over 6. That's going to just become pi over 2, of course. Minus 2 times the cotan of pi over 6. What I'm going to do is I'm going to draw my little triangle here. This is a 30-degree angle. I'm in the first quadrant. Again, you can call your rotating arm whatever you like. I like calling it 2. That means my shortest side, the side opposite the 30, is half of that. And the side opposite the 60 is that short side times the square root of 3. Cotan is the reciprocal of tan. So cotan is x over y, square root of 3 over 1. And that's how I got my final answer. Okie dokie. I hope that was helpful.